Hello folks, and welcome to this video, which is going to continue our journey into talking about the surface area of cones and pyramids. We're going to start by refreshing ourselves from the last lesson, how we find surface area when we're given slant height. So in this scenario, we're given the radius is 3 inches, and then we were also given that slant height. Remember, that was the height on the surface of the solid, and remember, that's what we really care about for surface area because it is on the surface. Our formula for surface area of a cone was pi r squared plus pi times r times L. L represents the slant height. The pi r squared portion of the formula is the bottom circle, it's the base, and then the lateral area is pi times r times slant height. Once we write out our general formula for surface area of a cone, we're just going to substitute in the values from the diagram, simplify our terms down, and then combine our like terms, making sure that we include the units squared, inches squared. Today, we're going to continue on. This time we're going to be given the radius, but instead of given the slant height, we're given the height of the figure going through the solid. So it intersects the radius at a right angle, and we call that the height of the solid. So it's not slant height, it's just height. And in this case, it's going to be 4 inches. Now, because we're talking about the surface area of a cone, it's still going to have the same formula, but we need to have the additional step of solving for like, what is the slant height? I need to figure out what L is. Well, if you notice, the slant height, the height, and the radius form a nice right triangle, and it's essentially what we've been doing the whole year, right? If I see a right triangle, I know the Pythagorean theorem is true. A squared plus b squared is c squared. It's important to note that in this scenario, the c value is opposite that right angle, so it's going to be the slant height. So the height squared plus the radius squared is L squared. You're going to substitute in your values, simplify down, take the square root, and you get that the slant height is 5 inches. Now, once you go through that additional step of Pythag to get the slant height, we're going to use that value and go back to our original formula. So when we're given the height of cones or pyramids, you have to make sure that you do that Pythag problem to get the height, that's the slant height on the surface. So you substitute in your values. Notice that we don't substitute the 4 in at all. It was a tool that we used to solve for the slant height. You simplify down, you combine your like terms, and then make sure you add in units squared. So it's really important to note that these are not the same problem. Yes, they have the same numbers, but they're definitely not the same problem. The one on the left, they give you the slant height, the height on the surface. You just substitute the 15 into the formula and you can solve. The one on the right, they give you the height of the cone. And in that scenario, you have to go through the additional step of the Pythag to solve for the slant height on the surface. And then you would use that value to find the surface area of the cone. So do not be that student that just looks at these problems and thinks they're the same, because they're completely not. So right now I want you to go ahead and pause the video and complete this sentence. The difference between slant height and height is... Okay, folks, welcome back. The last thing we're going to talk about in terms of this is in terms of pyramids. They can be a little bit more complex because remember, their bases can get kind of fun. We'll say that it gets fun, especially when we're talking about regular polygons. So here I have the height drawn in and the slant height. Once again, we're interested in finding the slant height for surface area because it's on the surface, right? It's that height of the triangle for the lateral area. If I connect the height segment to the length segment at the bottom here, notice that it forms a right angle with the height. So you have your right triangle there, and you're going to use Pythag to solve. But the issue is like, well, what is this red segment on the figure? So if I take that pentagon and instead look at it in a two-dimensional view, notice that that red segment connects the center of the pentagon to the midpoint of the opposite side at a right angle. Do you remember what we call that segment? It might be easier if I sketch in those triangles that we use. Notice that it's the height of the triangle that we're going to use for finding the area. We call that segment like the apothem. So when we have a pyramid, instead of being the height squared plus the radius squared equals slant height squared, now it's going to be the height squared plus the apothem squared is the slant height squared. We're going to go ahead and jump into a couple practice problems, and then you'll be on your way. Here is our first practice problem. Notice that before I do anything, I'm going to identify the pieces that I have. So right now I notice that the 10 is the slant height of the triangles. I'm going to use that when I'm finding the lateral area of the pyramid. And then I'm also given the height going through the pyramid from the apex or the vertex to the center of the hexagon in this scenario. The first thing I'm going to do is probably find this length here. Remember that if I'm connecting the center to the midpoint of the opposite side, that's the apothem of the hexagon. So you can label it any variable you want. I'm going to label it A for apothem. And then notice here that I have a right triangle inside this pyramid, and I'm going to use that information and substitute into a squared plus b squared equals c squared. So I have the a squared plus b squared equals c squared. I'm going to leave a to be the apothem. The b value, well, if the right angle is right here, the hypotenuse would be the slant height, which is 10, so that means the b value is going to be the 8. A good way to check your work is if you're getting a negative answer, you probably set up the Pythag wrong. A squared plus 64 equals 100. Subtract to one side, and then you take your square root of both sides. And you should get that the apothem is 6 meters in this scenario. Now, we're not even close to being done finding the surface area. So once I get that piece of information, I'm going to redraw the hexagon, the hexagonal base. So this figure at the bottom here, I'm just going to redraw that. And then remember that we found the length of the apothem, which is cutting through the figure and connecting the midpoint to the center of the hexagon, and that distance we said was 6 meters. Once I do that, we're going to go through our whole process and divide into our triangles. We need to find the measure of the central angle. So 360 divided by 6 means that the central angle is 60 degrees in here. But remember that when I find that central angle measure, I'm going to bisect it because I'm working with the right triangle. So I'm going to cut out that yellow triangle. I see that the height of it is 6. If I take 60 and it's bisected, this angle is going to be 30. This will be a right angle, which would make this 60. Now, when I'm talking about the area of a hexagon, I'm interested in finding the length of the base. So I'm going to call that lowercase b. And then from there, we have a 30, 60, 90 triangle. Remember, it has a ratio of 1, root 3, and 2. Right now, we have opposite the 60 is 6, and we need to find the length of the base. So when we're going that direction, you're going to take the value of 6 and divide by root 3. So you're going to get 6 over root 3. Remember that when you do that, you have to rationalize. So I'm going to take the top and the bottom and multiply by root 3. And then that's going to become 6 root 3 over 3. And then recall that you always want to check the numbers outside the radical and see if you can reduce those. So in this case I can. 6 divided by 3 gives me 2 root 3. Now recall that if I go back to the triangle, that represents this part, or in other words, this length is 2 root 3. So that length is 2 root 3. Then the whole base of the triangle is going to be 2 root 3 plus 2 root 3, which is just 4 root 3. You add them. Okay. Once I get that value, I'm going to probably find the area of the hexagon first, since I'm mostly there. I'm going to start by finding the area of one triangle, so it's going to be 1/2 times, I want the full base, so the full base was 4 root 3, times the height of the triangle is this value right here, that's the 6. And then you have to make sure you multiply by how many triangles you have on the figure. And there are 6 of them. So the area of the hexagon, which is the base, is going to be 0.5 times 4 times 6 times 6, which gives me 72. And then I need to make sure I don't drop the fact that there's that root 3 meters squared for the hexagon. Now go back and look at the pyramid. How many hexagons are on the pyramid? Just 1. So I'm going to save that answer and add it at the end. The next thing I need to do is find the lateral area of the pyramid. So far I found the area of the hexagon down here, but I need to find the area of all of those triangles. So what I'm going to do is I'm going to highlight that in probably green. It's that green triangle right there. Now I see that the height of the triangle is a slant height, which is 10 meters. So I'm going to draw that in. That's 10 meters, but I don't know the base of the triangle. However, we did solve it when we were solving for the hexagon. Notice that for the hexagon, it's a side length of the hexagon. All of these are the same. So if I go back, the side length of the hexagon we said was 4 root 3. So this base of the triangle is actually 4 root 3. Once I do that, I'm going to find the lateral area, which is going to be 1/2, because it's a triangle, times the base, which we said was 4 root 3, times the height, which is 10. And then you have to multiply by how many triangles we have. So if I look at the pyramid, there's 6 different triangles, so I'm going to multiply by 6 of them. So for the lateral area, I'm going to do 1/2 times 4 times 10 times 6, which gives me 120. And then you can't drop that root 3. And that's going to be meters squared. So still not done. This is so fun. I have my lateral area here and my base area, which is the hexagon. The last step is to just simply add them. So my surface area is going to be 120 root 3 plus 72 root 3. Now, because both of these expressions have that root 3, because you're multiplying by the same number, you can combine them. So my final answer for surface area is going to be 192 root 3 meters squared in exact form, and then you're good to go on. Looking at this next example here, we have a cone. So I'm going to start by writing out the surface area formula for a cone. It's given by the area of the base, which is pi r squared plus pi times r times L. Now notice here that this time they're giving me the height going through the cone as well as the radius. I need to do Pythag to solve for the slant height first. So off to the side here, I see that I have my right angle in that corner, which would make the slant height the hypotenuse. So I'm going to do 7 squared plus 6 squared equals the slant height squared. Simplify down. And then you take your square root. So I wound up getting that my slant height is the square root of 85 inches. Once I get that to be my slant height, I'm just going to go ahead and substitute that into my formula. So I'm going to say pi. The radius here is 6. And then I'm going to substitute in the square root of 85. I'm going to simplify down. 36 pi plus. Now the question becomes like, what do I do with this? I personally prefer you to write the square root at the end, so that way it doesn't look like the pi or the number is getting square rooted. And this would actually be your final answer once you attach units, inches squared, for surface area of this cone. So it's perfectly fine not to combine those things because you're multiplying by root 85. You actually cannot. So your final answer would be 36 pi plus 6 pi root 85 inches squared.